Okay, so hello everyone, my name is Yun-Sheng. Today I'm going to talk about verifying vMVCC, a high-performance transaction library using multi-version concurrency control. We like transactions because they abstract away tricky concurrency for the application developers. However, this also makes the application performance largely depend on the underlying transaction layer. And to achieve high performance at the transaction layer, we need to employ sophisticated concurrency techniques, such as multi-version concurrency control and contention-free data structures. But getting them right is hard. Pryware has discovered many bugs in the transaction layer of mature systems. This bug can lead to severe consequences such as corrupted databases, data losses, security issues, and etc. Our approach to this problem is formal verification. At a high level, formal verification is about establishing the connection between the implementation, the specification, and the proof. If the proof checker gives an OK, then we know the implementation conforms to the specification. In this work, the implementation is a transaction library that internally uses vMVCC, which has two important features. First, it keeps multiple versions to improve concurrency. And second, it uses timestamp to order each transaction. Then we prove the implementation against a strong specification called strict serializability. So what guarantees do we actually get when a proof checker says OK? The most important guarantee we get is that transaction must execute in some strictly serializable order. This also implies that a wide range of bugs are eliminated. This includes race conditions, out-of-bound accesses, off-by-one errors, incorrect GCO versions, violation of timestamp monoticity, and etc. Of course, there are a few challenges to this approach. First, we need a specification for strictly serializable transactions. Second, we need to prove that vMVCC transactions appear to execute in some total order, despite in the underlying implementation, it might perform sophisticated reordering to achieve high performance. Finally, we also need to reason about practical features and optimization regarding versioning and timestamp, such as garbage collection and RDTSC-based timestamps. The main contribution of this work is a system called vMVCC, which is the first vMVCC-based transaction library with a machine check proof of correctness. vMVCC itself is a high-performance in-memory transaction library implemented in Go. It includes a GC procedure to reclaim unusable versions and a highly scalable timestamp scheme using RDTSC. Its formal specification is succinct and application-friendly. On the proof side, one highlight is its use of privacy variables to formally reason about the linearization of vMVCC transactions. For the rest of the talk, I'll first introduce what is vMVCC, and then highlight some interesting aspects of the spec and the proof. I'll introduce vMVCC with a concrete example, but to see what good is vMVCC, let me begin with a more conventional approach to enforce a total order using two-phase locking. So in the example, we have two transactions. Transaction A reads the key k twice, and transaction B reads k, and then increases the value by 1. While the reads of A and B can proceed in parallel, the write of transaction B will have to wait until transaction A commit, at which point the lock on k is released. To remove the stalling issue caused by locks, vMVCC keeps past values to improve concurrency. By keeping past values, the write shown on the example does not need to wait anymore, as what it does is simply appending a new value v+1 to the list of values of k. And most importantly, the old value v is still there. Moreover, to achieve a total order, vMVCC assigns a unique timestamp to each transaction when it begins. Each transaction then uses the timestamp to pick the correct version to read, and to write a new version with its own timestamp. So that's pretty much how the vMVCC protocol works. Next, I want to talk about how to formally specify a strictly serializable transaction. To do so, we first need to figure out what a transaction actually does. Intuitively, a transaction appears to execute its read and write atomically at some instant during the course of its execution. The point is also known as linearization point. For vMVCC in particular, transaction linearize exactly when timestamp is generated. The reason is that if a transaction linearizes before another, say A before B in this example, then every operation of A should appear to happen before every operation of B. And that is exactly what timestamps are intended to do. So with this intuition, we can think of transaction A and B execute their reads and write on the logical state at their own linearization point. But what is the logical state? It's actually surprisingly simple. It's just a current value for each key. From the example, we can easily see why a single value is enough. Right before the linearization point of A, the current value of K is V. So both read of A will return V. Since A does not modify K, the current value of K is still V before the linearization point of B. B will update K to V plus 1, so after the linearization point of B, the current value of K becomes V plus 1. Using this example, we can do a small generalization and get an informal specification for transactions. The generalization is based on the fact that transaction can atomically read and write multiple keys. So the spec basically describes how the transaction read and write a logical state around its linearization point. One interesting fact about the spec is that since the logical state is just a single value for each key, the versioning or the timestamp are not mentioned at all in the spec. This means that there are merely implementation details, and the proof would ensure they are handled correctly. Another nice thing about our spec is that it's application-friendly, in the sense that it reduces verification effort of application code. This is captured by the top-level theorem of vMVCC, which takes a sequential spec for the transaction body and give a concurrent spec for the transaction. What it means from the perspective of application developer is that they only need to reason about the transaction body in a completely isolated world where no other concurrent transaction exists. And the top-level theorem of vMVCC would ensure the safety to run the transaction concurrently with other transactions. So that's pretty much what I want to cover about the spec. Next, I want to talk about a verification challenge we encounter when verifying vMVCC. The challenge stems from the fact that MVCC transactions linearize before their body runs. And as mentioned earlier, we need to update the logical state at the linearization point. For instance, transaction B in the example should update the current value of K to V plus 1. But to do so, we need to know in advance what transaction B is going to do. In contrast, under two-phase locking, transactions linearize when they commit, at which point the updates are already computed by the transaction and therefore known to the proof. To address this challenge, we use a technique called prophecy variables. At a high level, we use prophecy variables to speculate whether a transaction commits or abort, as well as its update. With the speculation, the proof can update the logical state accordingly. But the speculation is more of a hypothetical thing that a program cannot physically access. So at the end of a transaction, the proof needs to reconcile the speculation with reality when the transaction commits or abort. But the tricky part of using prophecy variable is that we have to consider all possible cases, and some of them could be wrong. For example, here I show 3 possible executions of transaction B. The first one says that B will commit and update K to V plus 1, which is a valid speculation. But the second and third ones say something that doesn't actually align with the reality. At this point, what we should do is case analysis on all possible executions. Let's say we're in the first case. In this case, we'll simply follow the speculation. And since the speculation aligns with the reality, we can simply proceed and conclude this case. But for the second case, and similarly for the third case, the proof updates the logical state to V plus 2, which doesn't really match what this transaction will do in the future. But it's okay because when transaction commit and update K to V plus 1, we will be able to obtain a contradiction. Thanks to prophecy variables, we're able to prove MVCC transactions against the nice spec that we have. So what we verify is not just an abstract MVCC protocol, but a concrete Go implementation that is open source on GitHub and can be used independent of verification. The resulting program is about 800 lines of Go code. On the proof side, we use Goose to import the Go implementation into Perennial and mechanize the proof in Iris and Cork. The spec is 42 lines for Cork, which is much smaller than the program. The proof is about 11K lines of Cork, and the proof program ratio is on par with other work on verifying concurrent programs using an interactive serial improver. As a reflection, we try to answer the question, what good is the proof? The first benefit to us is that during the process of writing spec for the whole system and the internal component, we get a better sense of what they do and thereby leading to a better design. Moreover, writing the proof also encourages us to write cleaner code to reduce the proof effort. And of course, Writing the proof also helps us catch subtle bugs in our initial implementation. This includes premature GC of stale value version, violation of string monoticity timestamps, and several off-by-one errors, since the protocol is based around comparing timestamps. For the evaluation, we ask whether the performance of vMVCC is competitive to state-of-the-art unverified system. We choose a standard database benchmark to evaluate performance, including YCSB and TBCC. We run all experiment on an AWS EC2 instance with 36 vCPUs and 72 GB of main memory. We compare vMVCC to CSAIL, which is a state-of-the-art MVCC system. Here are the evaluation results. Depending on the workload, vMVCC throughput is within 25% to 96% of silos. Looking more closely, we identify two main reasons that lead to the performance differences. The first reason is the lack of a tree-based index structure in vMVCC. This means that to handle a range query, vMVCC will expand that into multiple reads, whereas CSAIL would simply issue a range scan that is more efficient. To confirm this, we run a workload where each transaction randomly reads 100 consecutive keys. vMVCC's throughput is about 1/2 of silos. So having a tree-based index structure will certainly help vMVCC performance in workloads that involve range queries. The second reason is silos' lower versioning overhead. Silos design create a new version only every 1 second, whereas vMVCC create a new version for each write. On the other hand, because of that design choice, CSAIL does not guarantee that its read-only transaction are linearizable. This means that read-only transaction can return stale result. In contrast, for vMVCC, a read-only transaction is simply a normal linearizable transaction that does not write anything. To confirm that versioning is indeed the overhead, we made an incorrect variant of vMVCC that does in-place update and therefore does not allocate new versions. And its throughput on the YCSB write-only workload increases from 38% to 87%. As for the related work, there are other formal frameworks for reasoning about transactions. vMVCC uses concurrent separation logic and therefore also inherits its benefits such as local reasoning and ease of composability. Prior work has applied privacy variables to verify small data structures and algorithms. vMVCC uses privacy variables to prove a complicated system implementation using MVCC. Lastly, the verification of vMVCC is inspired by other verified transaction libraries, such as GoTSN, which uses 2PL for concurrency control. vMVCC uses a more sophisticated concurrency control plan. To conclude, vMVCC is the first MVCC-based transaction library with a machine check proof of correctness. Its implementation is sophisticated to achieve high performance. It comes with a succinct and application-friendly specification. And its proof includes the use of privacy variable to reason about MVCC transactions. And that's it. Thank you.